The rules of the Collatz conjecture are simple enough for a child to follow. If a number is even, divide it by 2. If it's odd, multiply by 3 and add 1. Yet applying those basic instructions creates a mathematical pinball machine. A single number will shoot violently upward into the millions, only to crash suddenly back down to 1. Mathematicians have fed quintillions of starting numbers into supercomputers, mapping their exact paths, and every single one of them eventually plummets into the final 4-2-1 loop. But confirming quintillions of paths does not constitute a formal proof. To rigorously analyze the entire infinite sequence, computers have to calculate the eigenvalues of massive matrices. Standard numerical analysis handles this using floating-point arithmetic, which is essentially a system of highly accurate decimals. This chart shows what happens when running those decimals through hundreds of iterations. A microscopic rounding error at the origin might seem harmless, but as the sequence stretches on, that tiny deviation exponentiates, ballooning into mathematical noise that eventually swallows the whole chart. When dealing with infinity, a near-perfect approximation is still an error. To actually solve the sequence, you need a method that operates across an endless set of numbers without introducing a single microscopic inaccuracy. Escaping the trap of floating-point math means throwing out the decimals entirely. Proving the conjecture requires absolute, uncorrupted algebraic truth. To achieve that truth, researchers replaced decimal approximations with a technique called exact rational power iteration. Instead of estimating values with trailing decimals, the algorithm stores every matrix entry as an exact, locked algebraic fraction. Because infinite precision libraries handle these fractions, the calculation preserves absolute algebraic truth. Rounding noise completely disappears, creating a flawless mathematical model. With the noise gone, the algorithm constructs what is called a countable adjacency matrix. This infinite dimensional operator maps out a staggering 2 to the power of 123 distinct modular pathways. Because this matrix is structured around modular depth, it behaves as a compact operator, perfectly capturing the dynamics within a localized, finite block. Infinity is successfully caged inside a pristine fractional matrix. Now, mathematicians have a clean environment to isolate and measure the opposing forces at work within the sequence. Inside that environment, the Collatz map is driven by 2 competing forces: the predictable downward gravity, the signal, and the unpredictable erratic upward spikes, the noise. This diagram shows those forces breaking apart. The primary downward signal is the principal eigenvalue, dictating a geometric decay of 8/9. To measure the remaining noise, researchers use spectral deflation. By calculating a modified matrix, they surgically extract this dominant equilibrium from the operator. Subtracting that steady downward pull shifts the entire mathematical landscape. The erratic, chaotic subdominant eigenvalue, lambda sub 1, is now exposed as the highest remaining point in the deflated matrix. Trying to calculate the individual eigenvectors for an infinite matrix is computationally impossible. Instead, the algorithm relies on a shortcut using matrix traces, which is simply defined as the sum of a matrix's diagonal elements. When you take that deflated matrix and raise it to high powers, the largest remaining eigenvalue completely takes over the trace. By calculating these trace ratios to depth 123, the equation cleanly converges, exposing the absolute mathematical limit of the chaos, approximately 0.7285. Spectral deflation successfully isolates the sequence's chaos. For the first time, the most unpredictable, rogue trajectories are assigned a hard, measurable number. Placing the 2 isolated forces side by side, on the left, the downward decay, lambda sub 0, at 0.8889. On the right, the maximum upward spike, lambda sub 1, at 0.7285. Subtracting this chaos from the downward pull reveals the spectral gap, delta, at exactly 0.1604. Because every step of this calculation was built entirely on exact unrounded fractions, that 0.1604 is not an estimate. It is an absolute, rigid certainty that the gap is strictly greater than 0. Locking in a positive gap creates exactly what mathematicians call uniform moment control over the entire infinite sequence. That control mathematically guarantees that the chaotic upward spikes are strictly bounded. They are demonstrably and permanently weaker than the downward geometric decay of 8/9. It means that no matter how high a number bounces, no rogue trajectory will ever generate enough constructive interference to overcome that downward gravity. The infinite chaos of the Collatz map has been permanently boxed in. The mathematical gravity pulling everything down to 1 is inescapable, certified by absolute proof.